last part of chapter 10 is dealing with combinations and permutations and the fundamental counting principle, which you actually probably already know, you just may not know that that's the name of it. So to warm up, I want to kind of use this idea of the fundamental counting principle by showing a tree diagram. You know, all the restaurants that are doing these deals nowadays, TGI Fridays has a deal, it's 2 can dine for $20. It may not be exactly what I have here, but something similar, you know. So each couple who goes in to dine can choose 1 appetizer, 1 entree, and 1 dessert. How many different meal combinations can you create from the following options? So, you know, a restaurant might want to do this. If you look at the selections, there's not really 20 different dinners available, but they could say over 20 different combinations available under this menu special. Something like that. So let's find out how many different combinations we can make out of these options here so that we know how many different meals you could go for. Well, a great way to do this is showing a tree diagram, and if you're doing a standardized test and it's an open-ended question, that's one way that you could show your work. So let's see if you remember it. If you think about it, you're only going to choose 1 of each. So we could have a tree coming off of each one of these appetizers, right? So start your tree diagram with these appetizers. So you can choose nachos, you can choose buffalo wings, or you can choose spinach dip. Well, you can only choose 1 of those, and after you make that choice, how many options then do you have for your entree? Well, if you choose nachos, you can choose the petite sirloin, you could choose the Key West shrimp, you could choose the baby back ribs, or you could choose the dragon fire chicken, right? If you choose buffalo wings, what are your options? If you choose spinach dip, what are your options? Then from each entree, what are your options for dessert? Finish the tree diagram, then I want you to pause the video, finish the tree diagram, then press play to check it and make sure you got it right. Go ahead and pause now. So your tree diagram should look something like this. If we want to find out how many different ways or how many different meal combinations can be created, then you just have to count how many different paths you have. So if you figure from nachos, you could choose the petite sirloin and the berry cheesecake, or you could choose the petite sirloin and the paradise brownie. You could also choose the nachos, the Key West shrimp, and the cheesecake, or the nachos, Key West shrimp, and the brownie. You could choose the ribs and the cake, or the ribs and the brownie. You could choose the chicken and the cheesecake, or you could choose the chicken and the brownie. So just from nachos alone, we have 1, 2, 3, 4, 5, 6, 7, 8 different meals that can be created. If you start with buffalo wings instead of nachos, how many different meals can be created? Well, you have 8 paths here as well. And if you start with spinach dip, you have 8 paths here as well. So in total, we have 24 different meal combinations. So an advertisement for Fridays might be something like over 24 different meals you can order over 20 different meal combinations with this deal. So again, one way to do this is the tree diagram showing all the different paths. Now I know we don't really like to take all that time to do all that work sometimes, so a quicker way is to just use your fundamental counting principle, which is however many items you have, if you're only choosing 1, you can choose this 3 different ways. You would multiply that by however many different ways you can choose 1 of these. So it'd be 3 times 4 options here, times how many different ways can you choose your dessert? Well, there's only 2 options there. 3 times 4 times 2 is 24 as well. So there's another way that you can figure out there's 24 meal combinations. If you do this, this is the fundamental counting principle. Like I said, a tree diagram is another option and one way you could show some work. So let's go into that. The fundamental counting principle says if there are m ways to choose a first item and n number of ways to choose a second item after the first has been chosen, then there are m times n ways to choose both items. Make sure you fill those lines in. So we had 3 appetizers and then we had 4 dinners. It would be 3 times 4 for choosing those. That gives us 12. And then we have 12 beginning of the dinners, and we have 2 desserts, so 12 times 2 to give me the 24. The fundamental counting principle is also kind of known as a permutation. And it's a great way that we can solve some problems without using the permutation formula, which I will show you next. But first, let's put this fundamental counting principle into use. So let's say you have 5 runners running a race. How many different ways can 5 runners finish the race? Well, remember, you're going to have 5 people, and you have a racing, you have a finish line. So if you think about it, there's 5 slots that we're worried about after this finish line, right? How many different ways can somebody, one of these runners, finish first? Well, you have 5 options for that first place. But now, once somebody has finished first, how many different ways can somebody finish in second? Well, if this person crosses the finish line and they're in first place, there's only 1, 2, 3, 4 options left for second place, right? How many options are there for third place? There's only 3 people after 2 people finish the race. There's only 2 people left for fourth place, and there's only 1 person left then for fifth place if there's only 5 runners to start with. So how many different ways can 5 runners finish a race? 5 times 4 is 20, times 3 is 60, times 2 is 120, so 120 different ways. Now I added another example in. I want you to do this under that part as well. I add this in as a B. Well, same race, how many different ways can 5 runners earn a first, second, or third place medal? So now in this case, not everybody's going to finish the race. I just care about who's in first, who's in second, and who's in third. So again, how many options do you have for first place? 5. Once 1 person finishes, there's only 4 options left for second place. Once both of those places are already in, there's only 3 people left running. There's only 3 potentials for third place. So in this example, you're not doing all the numbers. I just wanted to show it to you because you don't always worry about everybody finishing. The problem might only ask you for a certain part. So in this one, 5 times 4 is 20, times 3 is 60. There'd be 60 different ways that out of these 5 runners, they could earn first, second, or third place. So there were 2 words in the learning target, and you may not be familiar with them: combinations and permutations. A combination is a grouping of outcomes in which the order does not matter. So the outcomes where order does not matter. Where a permutation is an arrangement of outcomes in which the order does matter. So make sure you fill those in. So one real-world example that I think of that's actually wrong would be your locker combination, right? If your locker combination is 5, 20, 18, does the order matter in which you put that in? Yeah, you would have a different code. If you put it in the wrong order, your locker would not unlock. So actually, a locker combination should really be called a locker permutation because the order matters. Whereas, what's an example of a combination then? You know, if your teacher's dividing the class and they just want to choose a group of students to represent the class. If the order doesn't matter in which I choose Susie, then Ben, then Michelle, that's the same group as Michelle, then Susie, then Ben. So the order doesn't matter there. That would be a combination. So think of combinations with groups. Think of permutations where the order does matter. Another example I can think of is, you know, if you're ordering a pizza, if you tell the restaurant that you want pepperoni and onions, they're going to make the same pizza if you told them onions and pepperoni, right? So the order doesn't really matter there. So let's practice identifying combinations and permutations. In example 2, I just want you to tell whether the situation is a combination or a permutation, and then find the number of possible outcomes. So for the first one, an English test contains 5 different essay questions, and you have to choose 2 to answer, so it's your choice. Would this be a permutation or a combination? Well, you're choosing which 2 you want to do. It doesn't matter which one you choose first, so this is a combination. You're choosing a group of essays. How many different ways then could you choose it? Again, a diagram might help, or you could list it out. I like to show a diagram for this one. So if you think about it, maybe you have essay 1, 2, 3, 4, and 5. And you have to choose 2 of them. You could also show, you know, like we did with the tree diagram, you can show a chart to help you. So I could choose essay 1 and 2. I could choose SA 1 and 3, 1 and 4, or 1 and 5. If I choose 2 and 1, that's already here, because 2 and then 1 is the same as 1 and then 2. The order doesn't matter. So I'm not going to draw a line there. I can't choose 2 and 2 because that would be me only doing one essay. I can choose 2 and 3, 2 and 4, 2 and 5. So I had 4 options here. I had 3 options here. If I start with essay 3, I can't do essay 3 and 1 because I already have 1 and 3. 3 and 2 is already there because I already have 2 and 3. 3 and 3 is only one essay, but I can do 3 and 4. I don't have that drawn yet. And I can also do 3 and 5. And then if I start with essay 4, the only one I don't have already mapped would be to do 4 and 5. 5 has already been paired with every number right here, so I'm done. So I have 4 plus 3 plus 2 plus 1. I have 10 ways you can choose this. Again, you could just list out all the different pairs to help you as well. And then for B, you and 2 of your friends go to see Romeo and Juliet. How many ways can you 3 be seated in 3 seats? So I have 3 people and I have 3 seats. I want to know how many different ways they can be seated. Does the order matter here? Yeah, that's exactly what I'm talking about. I want to know how many different orders can they be seated. With the permutations, you can use the fundamental counting principle. So think about your 3 seats. How many options do you have for the first seat? 3 people. Now once somebody is sitting, you only have 2 options for the second seat. And once 2 people are sitting, you only have 1 person left who's going to sit. So there are 6 different ways that this can happen. So a permutation uses that fundamental counting principle. With a combination, the problems that you're going to do, you can map it out or write out the different possibilities like we did with this chart. The last part of the lesson is going to be the permutation and combination examples. I'm going to put this in a second video so I don't get cut off. So go ahead and move on here.